In this video, we are going to go over the role of the nucleophile in substitution reactions. So last time we talked about the stereochemistry in substitution reactions, and before that we had talked about the role of the electrophile in substitution reactions. So now we're going to look at the nucleophile. Now let's start with SN1. So I'm going to start by drawing a reactant that has a leaving group and a nucleophile. So this is dihydrogen sulfide. And I would like you to take a minute to draw the rest of this reaction. So you can pause the video to predict what will happen in this reaction, and when you unpause, we'll go over it together. Okay, so remember in an SN1 reaction, the leaving group leaves first, and we end up with a carbocation. So for this reaction, we would end up with a tertiary carbocation. And then we still have our nucleophile, and we've also formed our leaving group ion. Okay, so in the second step, the nucleophile is going to donate electrons to the electrophile. And we end up with a product that looks like this. We've got some hydrogens here. And again, we still have our leaving group that is negatively charged. Now, are there any formal charges in our first product? Yes. So let's look at that sulfur in our product. So sulfur normally has 6 valence electrons, and here it only has 2 lone pair electrons. And then we subtract half of the electrons that it's sharing, which is 2, 4, 6. Okay, so that's 6 minus 2, which is 4. And then 4 minus half of 6 would be positive 1. So that sulfur actually has a positive charge. And typically, if an atom can be neutral, it will be neutral. And conveniently, we have a negatively charged leaving group. So that leaving group can actually grab on to one of the protons on sulfur. So let's show that. And then electrons will be left behind on sulfur. So I'll just draw the products down here. So we would eventually end up with let's see, H bonded to the leaving group. Okay, so those would be our 2 products at the very end. So if you got most of the way there, good job. And then that last step was kind of a challenge step. Now, what type of product do we have? So if we have a sulfur in a molecule, what type of functional group is that? So this is called a thiol. So remember, if you have a sulfur in your product, or a sulfur in general, that is a thiol group. Okay, so now let's look at a slightly different reaction. We're going to use the same electrophile, but we're going to change our nucleophile. So this time our nucleophile is water. Okay, so if you want to pause the video and try to draw this reaction yourself, feel free, and when you unpause, we'll go over it together. Okay, so let's draw this reaction mechanism. All right, so similar to before, the leaving group leaves. And then we end up with our carbocation. And our nucleophile stays the same, and then we have our leaving group. Okay, so similar to before, the nucleophile comes in and forms a bond with the carbocation. Okay, so are there any formal charges on our first product? Yes, so similar to sulfur up above, oxygen would have a positive charge here. So in order to alleviate that positive charge, the leaving group, which is negatively charged, can grab onto a hydrogen. And then those shared electrons are left behind. Okay, so we end up with these two products. And when hydrogen bonds to the leaving group, that takes away its negative charge because it's now sharing those electrons with hydrogen. All right, so what type of functional group do we have in our first product? An alcohol. So that one we've seen a lot. Okay, now let's talk about the role of the nucleophile in an SN1 reaction. So we do have two different nucleophiles here. One has a sulfur, one has an oxygen. So is that going to have any sort of effect on the rate of the reaction? Nope. So let's think back to what the rate of an SN1 reaction is. So I'm going to write that in blue. So remember, the rate law for an SN1 reaction is equal to the rate constant times the concentration of the substrate, which in this case is the molecule with the leaving group. So is there any dependence on the nucleophile? None at all. So the nucleophile does not affect the rate of an SN1 reaction. So these two reactions actually occur at the same rate. So let's write that down. So the nucleophile has no effect on rate for SN1. So A and B have the same rate. Okay, easy peasy, right? Okay, so now let's look at SN2 because this might be a little different. So let's draw an electrophile with a leaving group again. And let's draw a nucleophile. All right, so if you want to take a minute and draw what happens in an SN2 reaction, you can pause the video, and when you unpause, we'll go over it together. Okay, so remember in an SN2 reaction, everything happens at once. So the nucleophile attacks the carbon neighboring the leaving group, and then the leaving group leaves. And our products, in this case, would look something like this. So this product is actually called diethyl ether. And this is something that's used in organic chemistry a lot in order to dissolve organic compounds. Okay, so now let's draw another reaction. Let's say we have the same electrophile, but our nucleophile is slightly different. All right, so if you want to pause the video and try to draw what the products are, you can. And when you unpause, we'll go over it together. Okay. So in this reaction, the same thing would happen. The nucleophile would attack the neighboring carbon to the leaving group. Leaving group leaves. And we end up with something that looks a little bit different than our previous product. Okay, so really the only difference here is the nucleophile. And do you think that there's an effect on the rate from the nucleophile? Yes. So remember, the rate law for an SN2 reaction is equal to the rate constant times the concentration of the substrate times the concentration of the nucleophile. So there is a dependence on the nucleophile here. So which reaction do you think would go faster? The first one, A, or the second one, B? So the first reaction would go faster, but why? Why would the first reaction be faster than the second reaction? So in the first reaction, our nucleophile is less bulky. So reaction A occurs faster because the nucleophile is less bulky. Or you could also say there's less steric hindrance. So this is actually really similar to what we've talked about previously with our electrophile. We said that for SN2, the electrophile should be less bulky, but additionally, the nucleophile should also be less bulky. And if a nucleophile is bulky, it's going to have a hard time coming in and forming a bond with the electrophile. So again, we do care about the sterics of our nucleophiles. So remember, sterics refers to the way that atoms are arranged. So if something is bulkier, it's going to have a harder time reacting. And again, this is just for SN2. Okay, so now let's talk about slightly different nucleophiles for SN2 reactions, because steric hindrance isn't necessarily the only thing that affects the rate of the reaction. Okay, so let's look at a reaction with our same electrophile from earlier, but this time we're going to have a reaction with a hydroxide ion. And then in reaction B, we're going to switch out that oxygen for a sulfur atom. All right, so if you want to take a minute and predict the products for each of these reactions and show the arrow pushing mechanism, feel free, and then when you come back, we'll go over it together. Okay, let's see what happens in these two reactions. So remember, with SN2, everything happens at the same time. So the nucleophile will attack the carbon next to the leaving group. The leaving group leaves. So in the first reaction, the OH group is just replacing the leaving group, and the leaving group ends up with a negative charge. In our second reaction, again, the nucleophile attacks the carbon next to the leaving group. The leaving group leaves, and SH is going to replace the leaving group in the product. Okay, so let's compare these nucleophiles. So again, we know that the rate of an SN2 reaction does depend on the nucleophile. We saw that on the last slide. But let's look at the difference between OH and SH. So which of those two nucleophiles is more stable and why? So if you remember back when we were talking about the stability of conjugate bases, that might help jog your memory. So if we think about these two as bases, as conjugate bases, which one is more stable and why? Or I guess which one is weaker and why? So it all has to do with atomic radius. So remember, the further down a column you go on the periodic table, the larger the atomic radius. Okay, so sulfur is further down the column than oxygen, but they're both in group 6A. So sulfur is larger than oxygen. So would that make sulfur more stable than oxygen or less stable? More stable. Remember, if atoms are larger, they can accommodate a negative charge better. And that's because the negative charge is actually spread out across the entire atom. It's not localized. So we've talked about this with iodine before. Iodine is so large as an atom, it can accommodate that negative charge. And that's actually referred to as polarizability. So can something spread out a negative charge better? If it can, because of its size, then it's more stable. So let's write down SH minus is more stable than OH minus due to its larger atomic radius. Okay, so if SH minus is more stable, does that mean it's going to react faster than OH minus or slower than OH minus? So remember, if something's more stable, it has less energy, so it's not likely to want to move or react compared to something that is unstable and has high energy. So you can kind of think about this like people, right? If somebody is low energy, they're just going to sit there. They're not really going to do much. But if somebody is really high energy, they want to go do stuff. They want to get stuff done. And maybe you categorize that as unstable. I don't know. But when we're referring to nucleophiles, if something has more energy, it is more unstable. So OH minus is less stable, so it is more energetic and more likely to react. So, which reaction is going to occur faster, A or B? A. So reaction A will, let's see, I'm running out of room, occur faster. All right, so we saw a couple of different examples of how a nucleophile can affect the rate of an SN2 reaction. But let's go to our summary table that we had started to fill out last time. And let's write down how a nucleophile affects the rate of an SN2 reaction and the rate of an SN1 reaction. Now, for SN1, we said that the nucleophile doesn't matter because the rate of the reaction does not depend on the nucleophile. So we'll just write does not matter. So that's easy. But for the SN2 reaction, it's different. The nucleophile does affect the rate of the reaction. So for an SN2 reaction, we would prefer a nucleophile that is less bulky and unstable. Okay. All right, so we've covered a lot of stuff about SN2 versus SN1 reactions. In the next few videos, we'll talk about leaving groups and the solvent. I will see you then.